Hello, can you hear me well?
Yes, yes.
Thank you for having me. And thank you, Sergey, for an interesting talk. And although I could not attend all it, but I really liked your conclusion about easier and simpler methods, which might be better than more complex methods. And I hope that my presentation will further enforce and maybe confirm this this idea, this line of thinking. I will speak about taxonomy enrichment task, and this is based on 3 publications we done recently with these 3 nice researchers. Varvara Logachova, who is a research scientist in SkolTech, Irina Nikishina, who is a PhD student in SkolTech, and Natalia Lukashevich from Moscow State University. So this work is based on originated from the shared task, which we conducted at Dialogue Evaluation, which was done for English language, but then we extended the setting of the task for English as well, and published this calling publication. And finally, there is also some further work on extending this on using some graph-based representations. I will mostly today speak about these two works. All right. So why should you care at all about taxonomies in the era of deep learning and end-to-end learning? Well, there could be still many reasons. Think of some Amazon taxonomy of products or some knowledge bases, which are usually contain some taxonomic backbone, so you can have many more examples. And these structures, they are some usually organized as kind of a trees or direct cyclic graphs. And they are usually also constructed manually. And this is the main strength and the main weakness of these resources. The problem with these is that you have to manually invest more and more resources and energy and time into maintaining these as to keep up with the changes in language. As we know, language is a dynamic system, is a grown system. It's not an artificial system. You cannot just fix it in a dictionary and say that's a language. So the people invested lots of energy in building such kind of resources, let's say for medical domain. But again, the same problem, even though they're quite useful, used in biomedical NLP, various applications, it's extremely expensive to hire doctors or experts to maintain them. So taxonomies are consist of hyponymy relations. Think of cat is an animal, jaguar is a car, and jaguar as also an animal. So this is very important to understand that this word senses would be problematic, and different lexical relations might lead to different hyponyms, to different abstractions. This is what makes the task of inducing taxonomies and mining them automatically not straightforward. So One source of semantic information which has been extremely influential and useful across various NLP tasks in the last, I'd say, 5 years was distributional semantics. But the problem is that the majority of words which you get through distributional semantical nearest neighbors are co-hyponyms. They are not hyponyms. So think of an apple and pear. They share the same hyponym, but they basically have co-hyponym. Just same siblings, but they are not synonyms. So this is an example for Russian language. This is an example for some hyponyms of different words. And one of the problems is that there is not all word senses might be present here, or not the senses which you might want to have in your resource. So you probably cannot just directly use these word embeddings and information from them just to complete taxonomy. You need something that in addition to this. And we will speak today of a few very simple but efficient and effective techniques which you can use to complete existing semantic trees dynamically, without much supervision, without much effort. Here is another example for related words. So you have similar words for the word mouse, and here you can observe that the distribution of word senses across nearest neighbors is extremely skewed, even though keyboard sense or program, some PC sense and rodent sense or animal sense, they are pretty much balanced. So it's not like you probably both know both of them, but usually it's not the same in the language. Usually you have a very steep distribution where you have a long tail of senses which are not at all common. So, but even here you see that among the nearest neighbors you have only 2 senses which relate to computer, and the remaining ones they dominated by animal. So that might be problematic if you want to create a balanced resource which cover all of them. Another interesting property of distributional models and distributional embeddings is how is the distribution of different semantic types among their nearest neighbors. So we had another calling paper which discussed this in more detail, and here the analysis for contextualized neural models is provided. So basically what is measured is that given a word net, we try to count how many relations of different types you have. Let's say the first relation of the first substitute generated by XLNet is a cohyponym if in the word net it was cohyponym. So this is how this graph was built, and you see that it's fragmented also for 2 different parts of speeches. And the trend is that if you take nouns, the majority of things you're going to generate through neural models, contextualized models, but actually it's more or less the same for non-contextualized models such as Waterback, FastText, Glove. They will be cohyponyms. Well, why they will be cohyponyms for nouns is because all these models are based on distributional hypothesis. So you have similar words occurring in the similar context, right? So And then you think for a moment about it, apple and pear and cherry and peas and other fruits, vegetables, they might appear in exactly the same contexts. And of course, they could be the word fruit, which also appear in exactly the same context as, let's say, word cherry and pear. But still, in a sense, just statistically in a language, there are much more these kind of cohyponym relations and cohyponyms than hyponyms, just by definition, because hyponyms are abstractions, so they are not supposed to be as numerous as their children in this tree. And this is the motivation why we need something to leverage the distribution information and then to structure it to reach the taxonomies. Here's another example from the same paper. And this is actually an example of contextual prediction, something which some participants of the shared task I'm going to describe, they performed. So in the shared task, the people were given new words and then a corpus where these new words appeared, and then they were supposed to then decide where to attach this new word in the taxonomy, given a bunch of context. So let's say you first time see in your life word selfie. So word selfie maybe was created or became popular around 2014 or 13, I don't remember exactly. And as a human, you probably can, from the context, just figure out on your own what this word selfie means. So, selfie is a kind of photo of yourself and so on and so forth. And I made a selfie with my dog. And then, gradually you figure out what the selfie means. And the setting of the task was basically similar. So you're given a bunch of words which are not present in the taxonomy, and a bunch of texts, and then you have to figure out where to connect in this tree the word. And so, what is the point of this illustration? Well, the point is that, again, you can see that the majority of nearest neighbors or contextual substitutes are not these bluish hyponyms. You see only actually one direct hyponym here and a few transitive ones, but the majority, again, they are cohyponyms. So this confirms this distribution hypothesis that you're going to have lots of this abundance of these cohyponymy things, maybe some unrelated words. So you cannot just take ExcelNet or some neural language model and then say I'm going to generate hyponyms. It doesn't work this way. But then what people tried to generate hyponyms before? The earliest approaches, tracing back to early 90s, is just based on rules, or lexicosyntactic patterns, to be more specific. So you have some syntactic construction, like apple is a kind of a fruit. And then, well, you don't really care about the fact that the word apple, you care about the construction that you have a noun and then another noun occurring in somewhere near this construction. And then, people figure out that it is possible to learn these patterns on the basis of some weak supervision and so on and so forth. And then, they started to try to mine hyponyms in this way. So representations for these patterns might be syntactic, might be just shallow, but yeah, this is more or less the same idea. And then also some distributional embeddings could be used. And then you can assume that, okay, you have this word to backspace, and then you can take like offsets between hyperonymy pairs and use this offset to add like in king queen style operations and obtain desired results. And then you can possibly combine these in some supervised framework. So you can take embeddings of hypernym, embeddings of hypernym, and train, use these concatenations of features, train neural network or classifier of your taste. And this is another branch of approaches which we used to detect binary hypernyms. The projection learning is another branch where you basically take an embedding of word, and then you perform an affine or nonlinear transformation to its hypernym. So you don't really need a feature of this or a candidate. You just project, right? And what people done, they organized a few shared tasks to detect how well you can extract hypernyms. So the tasks were mostly early tasks were mostly based on pre-computed candidates. So you're given, let's say, word mouse, and then you have 5 words which are hypernyms of mouse, and then 5 words which are random, and then you kind of need to classify them all. Later, people started to form this as a ranking task. And this is a more realistic task. In the ranking task, you're given entire vocabulary, and then given a single word, you are supposed to retrieve really some hypernym. So this is more useful in practice. And there was one task which is more similar to what we do, Semantic 2016 task 14. This task stated the following: okay, we have some taxonomy, and taxonomy can be incomplete. What we want to do, we want to add new senses to this taxonomy. So our setting is slightly simpler in the sense that we don't deal with senses, we deal with individual words. And this was done for English, and we also extend this for Russian. So there is some evaluation. In this evaluation, the interesting thing which has been done is that 2 versions of Russian wordnet was used, and basically the 2 snapshots of these wordnets were used to build gold standard. Some real annotation, real lexicographers actually worked over about 2 years, and then they performed this taxonomy enrichment by hand. And then this second snapshot was never published, at least at the time of competition, it was not published. And so the task was actually, hey, can we actually do the same as people done, but automatically? So we took 2 diachronic snapshots of lexical resource, and then we tried to, and then we given a corpus actually to participants, which people also used to figure out the senses of the words. So it's a kind of a new corpus. And then we try to ask whether we can build a machine which can do the same, which can figure out the meaning of new words and attach them in the right form. And this would be basically the setup. I will omit a few technical details, but for the evaluation purposes, we filtered a bit what kind of words we include. So we included only single words, and to make things easier, we didn't include some very short words for their large ambiguity. And the idea was that, okay, we got a total number of nouns here, and we provided some train set, and then performed a private-public split, which was used by participants. Well, this is a split of across different new words. Here is an example of a bunch of words which participants had to attach. So let's say we don't have in our resource some verbs or some kind of reverse, and then we're going to find the right place in this the semantic tree where to attach them. And what has been done in this calling paper is that we then thought, hey, WordNet also has different snapshots. We had WordNet 1.6, 1.7, and so on and so forth. And we can do the same trick by just taking the deltas between these different versions of WordNets. And then we generated 3 additional data sets, which basically do the same thing as we done for WordNet 1 and WordNet 2, and then we attained the second diachronic version, but now for English. For the evaluation, we used MAP, and well, we actually created a specific version of MAP, which says the following. It is sufficient to attach a word to some sense, at least. So if we have a connected component and it's sufficient to make only one link, if this link is basically covers the entire sense. If you have 2 gold standard relations, well, you have to link to both of them. And the Basal approach is very simple. It works like this. So we took fast text embeddings, and then we represent each scene set. So scene set is a set of synonyms. This lexical resources, they compose not of words, but of senses, and senses are kind of cliques of synonyms. And then basically we take this clique of synonym, and then some the lemmas of these embeddings, and therefore we obtain some fast text representations of these embeddings, and then we take for an input word, you have the selfie word, and then you like top 10 closest scene sets in this space, and then we output most frequent hypernyms of this word, because every scene set, it has its known hypernyms. And why it works? Well, as you can see here, if we take nearest neighbors, they are co-hypernyms as usual, and co-hypernyms, they often share some common hypernyms. As you see here, we often have very common hypernym for these 2 different senses. So these are exactly the hypernyms we take. This is the reason why this baseline works. And then we took made 2 small improvements to this baseline. First, we introduced ranking, so we don't just pick random scene sets, but we rather weight them by this count, by the number of common co-hypernyms across this list, and then we also use this distribution similarity as a measure. So if some scene set is very similar to the input word, then we should take it more seriously. And then what we also found on the results of the participants on the shared task is that it's very useful to use features extracted from dictionary. So they don't necessarily overlap one-to-one to the senses, but still they can be of great use, and features extracted from various definitions. So if certain hypernym is present in definition, it's a very strong signal. Using this resource is nice and useful, as you see later. And the nice feature about dictionary, it's available in like 250 languages, and it's constantly updated. So it's not something you actually have to build yourself from scratch by these dictionaries. It's not machine readable. It's very machine readable, and you have it for free. And the best approach in the shared task used some additional features from machine translation, extracted from Google Yandex candidate pages, so whether this hypernym is present in a certain corpus. And apparently we done some ablation study, and it appears that this feature helped him to win, really, trying to use these Google Yandex search results, because it's obviously a very large feature corpus. But if you remove this feature, as you see here, it's actually you observe enormous drop in the performance. So the best results for nouns was this supervised model, and the best results for verbs was by David Dalle, and it was very similar to this baseline, but with the only exception that he used longer list for candidates. He used like 100 candidates, and he also done a little bit more tricks on reweighting of these hypernyms, but that's it. Otherwise, with this very simple unsupervised technique, you can obtain very good results. And as you can see, as you add Victorian features, you really get a huge boost in performance. And yeah, so that's why if you have them, good to use them. The simplest to solve is to predict nouns, predict some named entities, because they are usually monosemous, and it's very hard to predict some short words because they are very polysemous, and on average verbs are much harder to predict. But if you think for a second, hypernyms for verbs, this is something like much more hard to think of at all. Here is an example what the systems gives you. If you get a dancing master as a word, well, the system going to predict this dancer, educator, performer, teacher. So these are also this number of senses of the words, and this is a verb prediction. If you give the system to O, then it's going to predict you have to attach it under the exclaim thing. So the system works, but we were not quite happy with only this automatic evaluation. We performed manual evaluation. We picked a few words here, and then we manually evaluated precision at 10. And it seems that for Russian language, you can obtain up to 75% accuracy for top 1, which I think is a very nice result, as you can just think of it as like, if I get first result in the 75% of cases, I can just directly attach it to the resource. And of course, you need the post-moderation of these resources, but it's a huge gain, possibly huge gain in automatization of this work. And as we return to this table, you see that we try and fast significant, but also BERT embeddings, and BERT embedding did not really take off. So they performed worse. So returning to the message of Sergey, like sometimes simpler models were better. What happened? Why BERT just didn't work here, and FastTech was enough? The answer is in this table. Well, the majority of the words, they're monosemous, namely they have only one hypernym. So FastText is going to capture them, this dominant sense in its nearest neighbor, so you are fine. And here is just a few examples of the errors. One type of error is that just irrelevance, not possible to predict multiple senses, as I told before, and maybe some other kind of irrelevance, like too narrow, too broad. So word embeddings are not perfect, and some supervision is desired to attach this task to filter for this noise. So taxonomy enrichment is a cool task. I really encourage you to work on hypernyms on taxonomy enrichment, because it might be useful in very different applications. And interestingly, contextualized models didn't improve the results, but the reason is that in this setting, we mostly attached new words, and it was sufficient to attach it in the main sense. And the prominent direction for future work is to introduce some graph structure and embeddings of the graph itself into the task, and then to apply it to taxonomy. And then I just say one thing about this graph extraction. We performed a small experiments with GCN autoencoder, and the idea was to actually compare different graph embedding models like Poincare embeddings, Not2Vec, and GCN. Yeah, apparently The motivation for this is that Word2Vec only provides textual information, and lots of information is also provided in the graph, and these kind of simple fast text models didn't use it. Apparently, currently, these approaches only marginally improved the fast text result, but still, I think it's a very prominent direction. And if you're interested in the direction, I suggest you to look at this recent paper, Taxo Expand, which is also taxonomy expansion work, which used the GCN's graph convolution networks to perform some kind of taxonomy expansion, although they use a slightly different setting. But I think this is a very interesting idea, as GCNs allow you to perform prediction for new eigen-networks without retraining entire graph. All right, so this is it.